of using the ideas of system efficiency to solve a problem. Okay, so in this example, we're going to use an electric pump. One advantage of electric motors and pumps is that they're pretty efficient. Okay, so we're going to assume an efficiency of 0.78. And what we're going to do here is we're going to raise 22,250 gallons of water to a storage tank that's 65 feet above the level of the lake. Okay, and we're going to do this over the course of 4 hours. All right, so what am I thinking here? How do I solve this kind of problem? Well, let's consider this from an energy point of view and add in the efficiency part. Okay, so what we know is that there's energy required from the motor to raise the water. Okay, so how much energy does it actually take to raise the water? All right, and so we know we're going to have to apply the efficiency factor and actually get more energy applying into the pump than it would take to raise the water, because we're losing some of the energy due to the efficiency of the motor. Okay, all right, so let's think about that. All right, so if I'm going to raise water for a certain height, this is a potential energy change, right? So we can get the total energy that it's going to take to raise the water. Okay, so we're going to call that ET, right? That's going to be mgh. All right, so I'm going to need eventually the mass of the water. I know what gravity is, and I know what the height is. All right, so once I have that, how much energy is it going to take from the pump? Okay, well, what we know is that the output energy, okay, so that's going to be the total energy required to raise the water. Okay, so we take E pump and you multiply by the efficiency, and that's going to give you the total energy to raise the water. Okay, so it takes more energy. This will be a bigger number, okay, than this number, which is the total energy required to accomplish the task. All right, so eventually we will get to ET over eta. All right, and then we can convert energy to power by just dividing by time. All right, so that's the mapping through the problem. Now I get to the details. All right, so when I'm thinking about the details, I know that there's some unit conversions that are going to happen. All right, and one of the things that comes to mind for me is I remember that water is a density of 1,000 kilograms per meter cubed. Okay, so that's the density of water. So that tells me, wow, I could go straight to metric, all right, and use this fact to solve for the mass. Okay, so let's do that. So the mass is 22,250 gallons. All right, and what we then know is that in 264 gallons, I had to look this up, there is 1 cubic meter. Okay, and now we have this set up for the density of water because we know there's 1,000 kilograms per cubic meter. Okay, so we get this mass, right? The meters cancel, gallons cancel, and we're left with kilograms. So we get the mass in kilograms. Okay. All right, so next we need gravity. We know that. You're looking at my formula here. We got mass, we got gravity. And height, we need to change that to the metric system. So if I have 65 feet, you know how to do all this. 65 feet, 1 foot, 12 inches, and 1 inch, 2.54 centimeters, and 100 centimeters in 1 meter. Okay, so now we got the height in meters, and so from there we can calculate the total energy. Okay, so we're using a consistent set of units here. It turns out the energy after we calculate this, if I do mgh, this turns out to be 16.37 megajoules. Okay. All right. So from there, we can get the energy required of the pump. So you do 16.37 and you divide by the efficiency. All right. And from there, we convert to the power by taking the energy of the pump. I put a power of the pump. Okay. Energy of the pump divided by the total time. All right. And then I need to get the unit conversions to work right. I need hours to be converted to seconds. So I'll have joules per second, which is watts. Okay, so I know that in 1 hour there's 3,600 seconds. Okay, so when I go through that, I get 1.45 kilowatts as the answer. Okay, so you see my process here. I have to think about, the new part of this was this efficiency idea that when I have the pump, I have to supply more power to the pump to accomplish the useful work that I need from the pump. Okay. The other thing I wanted to point out to you is taking a look at how this works out in MATLAB. I like the idea of using units, the unit symbolic capability of MATLAB, because it forces you to think about how you're going to enter this to get the correct set of units coming out at the end. Okay, and it can save you work, because notice what I did here. I started with the number of gallons. Let me make this a little smaller. Okay, I started with the number of gallons, and I attached the units of gallons to that. All right, and then I just multiplied by the density, because I know that if you take the density and you multiply by volume, the units should work out where they cancel and you get back mass. Okay, and so that's what I did here. You just multiply these together, and MATLAB is taking care of unit conversions along the way. All right, so if I display, VPA is what we use to display the answer, and I do this unit conversion, and what I'm telling it here with the second argument, we've done this before, is to report my answer in pounds mass. All right, because if I was curious about pound mass, all right, I could have done it in kilograms as well, but I wanted to show you that you can use whatever thing that you want, and this will take care of the conversion for you. All right, so this converted to a certain weight in pound mass. All right. So if I had tried to put pound force there, I would have gotten something different showing up in terms of these units, okay? Because it would have been a derived unit, all right? So there have been extra terms in there using probably U.Gn, because the gravitational constant is involved with conversion between pound mass and pound force. Okay, so from there, my point is, you now take the total work, all right, you can report that in megajoules, and that's what's showing here, all right, and then I calculated the power in MATLAB by taking the total work required, dividing by the efficiency, and then dividing by time. From there, it's just a matter of choosing which unit that you want to show. So I've showed two different sets of units here for the power. The problem asks for the units to be reported in kilowatts, right? So 1.45 kilowatts. You can also convert this to horsepower, all right, because it's real common in the U.S. to buy pumps in terms of horsepower rating. Okay, so hopefully this example will help you think about how to manipulate problems in terms of efficiencies.